Today I'd like to explore a powerful C++ feature added in the 17 standard, structured bindings. Structured binding allows you to give names to tuple-like members, so for pair.first and pair.second, or just anything for your tuples, array indices, given names, and data members in specific structs and classes. There are restrictions on them that we will get into later. What we have on screen right now is an example taken directly from cppreference.com, specifically the structured binding page where they talk about binding a tuple-like type. We're also on cppinsights.io, created by Andreas Fertig. I hope I am saying that correctly. My apologies if I am not. Getting started, we have 3 variables, 0 initialized. Then we have a tuple, which is what we will be using for our structured bindings. It has some strange types: float, L value reference, char, R value reference, and int. And we are constructing it with x, move y, and z. The move is so we can have this char ref ref. And we have the actual structured binding. A refers to the float reference member. So we can see in this insight. A, float reference. B refers to our char ref ref. Notice that B itself is not an R value reference. It is a reference to the R value reference. This is due to the reference collapsing caused by auto. The actual type deduction here is a little complex and is the same as auto, but applied to each individually. I will not be getting into the type deduction in depth here because it is extremely complex, but I will be touching on it. So, C refers to int. Notice we have const with this, which is why we have a const int reference C. Now, one thing you might notice, A and B are not const in this scenario. We can very easily modify them like this, and the compiler does not care. We still set them equal, just to prove that this tool does in fact give compiler errors, since it doesn't really, it looks like it's just annotating our source. It will give us an error here because C in this case is const. The reasoning for this little discrepancy between the const and these other types that are reference types is the const is applying to these types themselves. Meaning, this const, we have a const reference to int, but we have a const float reference. What I am not referring to this type. This is not the type I am referring to. I am referring to something a little bit different that usually you don't see. Float reference const, which is different and might not compile. Yes. This is essentially what it is, but in this case it will not compile because it doesn't make any sense. You already can't change a reference. There's no point in having this const here. And the same for the R value reference. However, reference deduction is being applied there. So, let's see the type if we had a float pointer. So I will change this to properly have float pointers. and comment this out. And we see we have float pointer const reference a. Kind of a gross type. So let's see what happens. Let's try dereferencing a and assigning. What happens? This is okay, because the only thing that is const is the pointer itself, not what it is pointing to. So if I were to say a equals null pointer, doesn't like that. So getting back to where we were with our original types, a is referring to x, well, more specifically tuples first, member of x. B is referring to std move y, but inside this tuple. C is referring to z. Note that this does not make a copy in this case. However, we can use copying here. One thing you might notice though is char reference cannot copy an R value reference. It is a deleted copy constructor. So we will just move this back to this, and we do this. Notice type of C has changed. We now have an int refref. Why? Because this is a copy. A no longer refers to any of these. They are their own. If we modify A will not be equal to x if we were to modify it. They're just being initialized with those values. Although, because of how we have this set up, we are making a copy of a reference. A and B are still technically going to modify x and y. Just a little weird because we have this strange type. C, however, is completely disjoint from anything else. C is now its own integer by itself. Now that we've covered the basics of this tuple-like type, let's get into something a little more interesting. Arrays. We're going to, again, take directly from cppreference.com and steal their example, because they are great examples, and I'm unlikely to get them wrong if I just steal them directly. So, as you can see, this works completely with the array. One thing to note is we're creating a copy here where x is 1, y is 2. And in this case, we are creating references. xr refers to this 1, and yr refers to this 2. We are binding these two. Now, this is a C-style array. This is C++. This is gross. Nobody likes these. So let's move it to a std array. And we'll just make it a little more C++-like. As you can see, things do change a tiny bit with the R value reference types with these copies. Slightly different, but we can still do the same thing. Now, one thing we can try here is an array of size 1. And this still works. You can still do this. Nothing wrong with it. You can also do something like this partial. And as you can see, no, you cannot do partial. It has to be full decomposition. You cannot do partial decomposition. It is not allowed. Now, for our final basic case, we can do it with structs and classes. Again, we're going to be doing something similar to the CPP reference, but I am going to change it up just a little bit because they do use bit fields, and I don't personally like dealing with bit fields, and they make things confusing. So, what we can do is we have an S, and we will direct initialize it with some values. Don't forget to give your variables names. Compiler doesn't like when you don't give them names. And using our auto, we can get them right how we want. So, as you can see, we have our structured binding. This is, of course, making a copy of both the members. We can just add ref, and it will refer to them now. One thing that we should note is that the standard does not like certain things, like, for example, anonymous unions. Really doesn't like anonymous unions in this case. Run it, try to bind. That's the wrong error that we don't really care about. Let's try that again. So, cannot decompose class type S because it has an anonymous union member. You cannot use this technique with anonymous unions, which is unfortunate, but does make sense. Now, just to prove that it does not have to be a pod type, it can have different, functions, whatever you want. We're just going to return x1 with a get function. So this is no longer technically a pod type. It still works. Very nice. So we look at this and we think, well, why don't we just do s.x1? This is way easier. And I agree. In most cases, it is. But there are cases where this is extremely useful. And probably the most common one is range-based iterators. You noticed we have included map, but we haven't used it. Now we will be using it. Instead of map, int to int. Let's just call it foo, and we will direct initialize it with 1 to 1, and then 2 to 4, and then just another to have some fun. We make our map, and then we have our for loop. Let's do a const auto. Call it a pair because we can, and then do something with it. We compile this and we get some kind of gross output. It's unreadable as is, but we don't really care about it right now. So this is the normal way you would do it. Pair is of type const int reference pair, const stood pair of const int reference. Big old mess. Big old mess. And that's just what you're going to get with your range-based for loop. Now, the issue now is pair.first, pair.second. This is extremely gross. First doesn't tell you a single thing about what's actually there. Neither does second. It's pretty much unreadable in some cases. To get around this, we have a nice feature, structured bindings. They can be applied in this scenario because pair is a tuple-like type. So let's give it a better name, key value. As you can see, this will compile, and it is much, much easier to look at, because then I can just say something about the key, something about the value, whatever we want. Now, to be more accurate to our example, we have a base and we're going to call it a base and a square. And now we can refer to them as base and square. Notice const auto, just because I don't feel like modifying anything. It's just a little easier this way. But we can do something evil here that you might not expect. We can't assign here. Why? Because int is just a normal data. So nothing's just an int. Const gets applied to it. And if we were to try to do something evil, can't do it. Map doesn't like it. And map doesn't like it. Really doesn't like it. So const in this case is being applied here, unlike before. And this is nice. We can't modify things when we shouldn't, and that's how things should be. Another very nice use case is for when something returns a pair. So an example of a function that returns a pair is, I believe, foo.insert. And then we will give it some value, a pair to insert. So 416. And as you can see, we're not doing anything with the return value. If you want to be fancy, in place. But a common thing is you want to use the return value, and it's a little gross because you have to do if ret.second and then dot. Little gross. Not very fun. Is it not in place? It might not be in place. We'll just go back to insert. So it's returning a pair to an iterator and a boolean. Boolean being insertion successful or not. This again, not very fun. Ret.first, ret.second, I don't really like it. And I'm sure many people also don't like it and consider it hard to read. So what we can do instead, iterator success. Again, something very similar can be seen on CPP reference. If success, this is much nicer, much easier to read, much nicer. Now, another thing we can do is take advantage of a more recent feature again, where we can have initializers inside of if statements, like so. And then we can just do this. Very nice. And that is it for our structured bindings. Thank you for watching. Feel free to ask questions in the comments section. The link to the CPP reference article will be provided in the description. I hope this gives you some ideas on how to use and what the purposes of structured bindings, and I hope you have a great day.